I'm Jeff Christian, and I'm from Knoxville, Tennessee, and I've been working in the community under a project called SET, which is Smart Energy Technologies. And what I'd like to present is the first of a three-part series on what I've learned relative to improving the energy efficiency of homes here in Glasgow. The title of this first part is Lessons Learned from Energy Efficiency Retrofits of 50 Homes in Glasgow, Kentucky. Previous life was the director of the U.S. Department of Energy Buildings Technology Center at the Oak Ridge National Laboratory. I had about $15 million a year working very heavily on energy technologies, and about 75 folks both on staff and as subcontractors helping to do that work. Currently, I'm an energy efficient specialist, and I'm focused very heavily on training both the installers of equipment and homeowners on HVAC and the building envelope, which is referring to the roof, walls, and foundations of your home. I've written lots and lots of papers, reports on this subject. I'm certified Buildings Performance Institute evaluator. I've got a degree from the University of Wisconsin in industrial engineering. I mention that because this is a great example of what industrial engineers do. They interface technology and people and study how that can be done more efficiently. And this project is all about that, technology meeting homeowners and how they're using it and how we can improve on its usage. Also have a degree from in environmental engineering from the University of Tennessee, and I was also adjunct professor there where I would work with teaching architects how to design more energy efficient buildings. The outline that I'm going to follow is I want to explain my specific role in this multi-million-dollar project. One of the very important first steps was I selected the 50 houses so they would meet the criteria of our funding that came to us. And in essence, that was from an analysis of 2014 data, looking at that billing data and finding out which were the peak hours in each month. And if indeed no behavior change and no technology was done, it was very likely that these 50 homes were going to be financially more impacted than the average home. I want to talk to you about what the characteristics of these homes were, both before. We can benefit from that to see maybe you have some of those same characteristics that would benefit from enhancing, and how we did after the retrofit, how their performance is now. Very specific, we'll talk about the costs and what common opportunities we found in these homes and the solutions that we use to reduce these costs. The selection of these homes needed to be diverse. It needed to be small houses, large houses, low income, high income. It needed to be a cross-section of Glasgow housing because I was responsible for doing a model that would predict how this could impact the entire Glasgow community, and for that matter, how it could impact other communities that attempt similar endeavors. These characteristics of these ultra homes, I mentioned that ultra is the word that we used in the project, extreme energy makeovers or simply energy retrofits, all terms that are used to describe this. But the unique thing of these 50, of which there were a total of 330 in the project, is they not only got the battery for peak load shaving, the heat pump water heater, the programmable thermostat, they also got a package of energy efficiency, which sometimes was the HVAC replacement, envelope, both added insulation, air tightness, sometimes new appliances, kind of based on what that individual home needed to reach the energy goals that were in the project. We could not do houses that had either moisture or structural issues, and there were some that we would have liked to have done that fell into this category of potentially big impacts. But this project, in general, what you do is you solve energy problems after you've taken care of the structural and the moisture, and that wasn't part of this project. So the database had no names on it. It only had indicator numbers that I didn't know what they meant. But I did have what the hourly 2014, before this project, energy demands were, and what they would be as far as energy costs under the new rate structure, which had a peak load charge. And in general, these houses all have in excess of potentially had increases of at least 15%. So those were the ones that we ended up picking, and then made sure that we had a cross-section of size, as I indicated. The average floor area did vary quite a bit. Some were actually less than 900 square feet, very, very small, like little habitat type homes, and others quite large, 5,000 square feet of conditioned space. Age on average was 32 years. We had some new houses, just only 3 years old. Still found a lot of energy savings opportunity, even though they were brand new houses. And the oldest one we have of this 50 was 72 years. As a group, in the end, they provided a very good cross-sectional representation, and that's what we wanted, so we could conduct this model. So the other thing that we did is we evaluated the HERS rating, and that's the rating of the building, the home energy rating. So the lower the value, the better. 100 is about, on average, what new homes, spec buildings, if you will, were going in the area and around the country about 5 years ago. And so the ratings that we found just walking into these homes, we had some that were about that level, 99, but some were as high as 3 times that, 273. Those generally mean very, very leaky, very, very efficient buildings. So there's, generally these don't need sophisticated analysis to know that they need this, and this particular house was under restoration or anyway. But another thing that we hope everybody in at least the TVA area will be more familiar with is this E-score. That's a 0 to 10, 0 being very bad, 10 high being very good. And I'm going to point out how you could make a phone call and access for very low cost, if potentially no cost, E-score to do some of the evaluations that we did on this project. The bottom line, energy savings of these 50 houses, on average, we saved 29%. We now learned a little bit, and we know with less dollars invested, we could actually save more, in part due to what we learned with the housing here in Glasgow. This is based on a very detailed, calibrated model of the house, actually using some of the sub-meter data that we had on a few of these houses. Sub-metered means we knew exactly how much was used for the dishwasher, the refrigerator, the range, and things, the appliances in the house. And then we had detailed measurements of the air tightness, of the ducts, and the whole house. That's very important when you model a house, to know those values so that you can truly predict what actually happens in the field. What we did is took the average after our work all the way down to 83 for HERS, and in one particular case we almost cut the energy bills in half, and these were based on just fixed rates. After conducting the pre-retrofit on-site evaluations, we had a couple of interesting observations. That one is that, and again, not knowing who was in these homes, what fell out was a very large number of folks that were from 2 demographic groups. One was elderly living at home during the day, for instance, very hot summer afternoons when peaks occur, and young families that didn't have children in daycare. They were there and living during, again, these hot summer and early cold. They weren't at school, they weren't at work. So these are 2 groups that were happy to certainly shield from some of the initial impacts of a rate change. Another thing that is, again, not statistics, but very, very interesting, and possibly even a stronger motive for fixing houses than energy savings, is that we found potentially a pretty strong correlation between high energy bills and leaky houses, particularly to the crawl space, which is not very healthy air down there in some cases, to respiratory or pulmonary illnesses. And that's an interesting finding, and boy, reducing energy costs on an annual basis, $500 is fine, but reducing medical bills would be even bigger story. So it's something to keep in mind, and something that we'd like to follow up in the community with doing at a later time. A few kind of reoccurring observations on these houses is the houses that fell out were in low, wet areas and in rocky areas. Two areas that, by the way, didn't get gas lines because of those problems potentially. They also were problematic in that wet areas generally mean moisture problems in houses, and rocky soils generally means I can't do, say, a geothermal system as easily as I might if it's just hard to put the geothermal system in the backyard that's a rock as opposed to soft soil that I can easily dig trenches in. We found almost all the bathroom and kitchen fans that are in these houses, many of them didn't have any vents at all to the outside, they're just circulating. But those that knew to get the moisture and the odors out of the house would drop them into the attic, and sometimes not even outside the insulation in the attic. They were just holes that were problematic in the sense that the moisture wasn't going the right place, and they were also leaking back into the house. Almost all of them had unsealed, what they call panned returns in some supplies, and that's where instead of having a hard duct, they would use the cavities in the floor and the wall and just put a sheet metal, or in some cases just drywall, and blow air to heat and cool the house through those cavities. Notorious leakers, notorious problems. What's the problem? Well, you end up pulling air in and pushing it out through your crawl space and attic. Two undesirable places to live. We want to have a nice house. We don't want to live in an attic. We don't want to live in a crawl space. The other thing that was interesting is the kind of the way that a lot of houses were built for a long period of time here in Glasgow is the floor insulation was just draped over the floor joists and then compressed everywhere where the joists met the subfloor. So this is a sketch above a photo that pretty well depicts that, and it shows the problem that is in many homes. At a first glance, you think it's good, you think it's insulated. Well, watch carefully. If indeed you push that insulation right next to where those ceiling joists are, or floor joists, you'll see that it's fully compressed. And that leads to not only energy loss, it also leads to cold surfaces where you might see a lot of the mold and mildew growing in the crawl spaces that have that type of insulation. What we did after the pre-retrofit evaluations is we modeled the house as I indicated. We generated the HERS index. We had a floor plan. We took key photos. This was all very useful to develop the contracts to bring contractors in to replace the HVAC or to do the envelope retrofits that were necessary. We produced enormous lengthy reports on each of these houses, and it's very, very valuable if anything would be ever done to these houses into the future. And more importantly, it was nice guidance to follow up with a post-retrofit to see what got done and to quantify the benefits after the projects were installed. Some of the things, I'll get into more of these later, that routinely occurs is downlighting. These cans are if just the way that it was standard to put them in is you'd push all the insulation aside. They had you could many times see the attic through the hole in the drywall, and of course these were very, very leaky. They need to be sealed. There's all sorts of easy, low-cost solutions for doing that today. Little sealed cans that push right up into them, and many times we're not using incandescent, hot incandescent bulbs anymore. We're using much lower heat generating LEDs and compact fluorescents. If a person is going to be sent up into this attic to add insulation, go ahead, put R50. Make sure it's a real R50. Make sure there's what's called baffles, where the slope comes down to the edge or right above the wall. It's called the soffit. Those baffles make sure the air still gets from the soffit up into the ridge or gable vents, but allows as much insulation to still be there as you can. It gets compressed naturally unless you make sure that you use all that space. And you don't want to blow all the insulation and plug it up right there. So things that we train several contractors in town to be able to do that, and it's fairly easy to do. Some of the preliminary recommendations would be the plenum, where the air goes in to the return for the HVAC. If it's made out of drywall and wood, it's leaking. And so the bottom slide, you'll see where mastic is used to seal those very likely cracks that lead to air going in places that we didn't want it to go, and led to inefficiencies. We wanted to make sure that we use the best practices. So TVA had a very nice document for their E-Score program, which outlined to the QCN contractors. That's the language used to describe in the TVA area contractors that are certified to do this and do it right. And they serve as their own quality inspector, but it's nice to have in these projects an independent third party to come back and just make sure that day that particular person did it correctly. Our targets were generally inspired by our project that gave us some guidelines, and they weren't necessarily the best to pick up the full air tightness package, for instance, in a real live job. And when we did model it, we took full account of that, and that really tells us that we can do even better than the numbers I'm going to share with you if done outside this project. And that's what I'm trying to do here, is encourage a broader number of homeowners to do some of the same things that we did to these homes. Some of the things that we specified was the SEER, that's the seasonal energy efficiency ratio. Low is bad, high is good. What we found out there in many cases were 6s, 7s, and what we put in and what we'd like to see is something in the neighborhood of 16, 3 times better. Our values present, what they had, sometimes there was none, and what we wanted to bring up to. And the particular project called for in essence, only getting credit for air tightness when it was very, very bad, and you were successful in getting it very, very good. In reality, everything's good. I mean, you go in, and you can't go in with syringes, but you want to make sure it's much better than it was, and then you want full credit of it. So if done outside the project, that wouldn't be prescriptive. It would take full account of any air tightness that you did do in your envelope or your ducts. This is an example of this happens to not be in this community. It's a very efficient house, had no insulation whatsoever in the walls. It's been upgraded. Very, very high performer, but it had also a very poor SEER 6 next to it, and that's now since been replaced with like a 16. If one is concerned with not only annual but also peak energy, something that we found with the houses here is that in the case of a heat pump, you need twice the capacity to heat than you do to cool. So if indeed you go and buy a certain size unit to meet the heating load, well, the cooling load then, if it's not 2-speed, goes on and off, on and off. In essence, having a very high peak cause as a result of that. But the newer units actually deliver and use what is needed. So at the low speed, which in many cases would be all that these units would run and are running all summer, even in 90 plus outside air temperatures, they're using much, much less energy than these older units that go on and off, on and off, on and off. They just ramp up and match the load. We tried to get as much of that into the community as we could and into these houses, and something to look for in your decision to replace your heating and air conditioning system. I want to focus with some numbers on the last 12 that we did. They tend to be towards the end when we learned some things from the first set. They are a little bit larger, a little bit smaller floor area, around 1,500 square feet. The energy usage, 18,000 kilowatt hours. So if you use about a dime a kilowatt hour, which is roughly what Glasgow, for instance, and much of the TVA region is looking at for residential, that's about $1,800 a year. The model predicted a bigger savings here with the heat pump water heater included in the calculation. We ended up with like 37% instead of the 29% across all of them. And the HERS went down. This is a lot of numbers. I want to just highlight a couple of areas that I have the red circles around. On that top column you see there, that is actual 2014, we call the base, energy usage. So some of them had as much as 2,400 kilowatt hours or $2,400, and on average was at 17 kind of range. The next big circle there on the annual energy savings, on average, $664. Some almost $1,000 per year saving. That's money in the pocket that can be spent on other things other than energy. One of these houses was particularly poor performing on an energy basis, and the HERS rating on there was 273. That's the pre-HERS column in the red circle I have. That is, I've been at this for a long time, that's clearly a record. That's as high a number or poorer performing on our energy perspective that I've found anywhere. And that 83 I've already mentioned, that's the average that we've brought these down. I've already mentioned that some of them have as much as cut the energy bills in half. I mentioned a model that we use to report out the overall project that we wanted to do, and I use that model here to generate not only the estimated energy savings and cost savings from our 50 Ultra houses, but all the rest of the homes that in essence had heat pump water heaters and Wi-Fi controlled thermostats in them. And that number ends up being a total savings of energy, customer savings, of close to $90,000 a year. And we're also very relieved and happy to see that we broke smashed and very severely the goal for this project. We in essence beat it by about 50%. So that was all very, very good to us and to our sponsors that paid for this project. So many times when I would do research work, I would share it with peers and they would review it. When I got my thesis, it was a thesis review committee. I would like the community to evaluate what you think we've done here with this particular project. And there's my email. I'd like to hear additional ideas that you found in your home to save that we can use and share with the rest of the community on helping others save energy. So